Thanks.
Okay. Thank you for introduction. So the paper was written by scholars from Chinese Academy of Science. Somehow they cannot come due to visa issue. So it's a great honor for me to present a paper for them. The paper is about modeling the uncertainty in 2D moving target selection. Target selection is probably one of the most common and basic actions on modern user interfaces. One of the common cases for static target selection, but in fact, moving target selection is also very common, especially in the gaming context. For example, here in a shooting game, you often have to use a mouse or finger to select a moving object. Or in a video game, you use a finger to select the running football player. But selecting a moving object is actually a very challenging task. You can see here, actually because it involves two steps. First, you have to track the object. Second, you have to select it. It turns a one-step job for static target selection to a two-phase job. And also it has introduced high demand on the sensory motor system. So typically, selecting moving target understandably result in worse performance compared with selecting static target. And let's dive a little bit deeper in this problem. The essence of the challenge is that the motion of the object, because the moving part introduces a lot of uncertainty for when you reach the object. And also, due to influence of a moving, it causes problem for selection. And you can see here is the endpoint distribution for selecting a moving object. One obvious pattern you may notice is that the mean of the endpoint distribution is the lag behind the center of the target here. That's due to the moving object effect. And also it results in wider spread of the endpoints. And in fact, this is a commonly known problem, and there's many solutions have been proposed. One option is that you can change the original. You can, for example, previous work introduced a hold that you use a mouse button to first freeze the moving object and then select it. Of course, introduce some extra operation. Another approach is that you make some visual of the interface, like say you show the trace of the moving object that might help with the target selection, like the comet or the target ghost. But you can see here there's methods. They either require additional operations or change the visual appearance of object. So for this work, they use a new approach, a model-based approach. The idea is that they first try to predict the endpoint distribution of the moving target. And then based on that predict distributions, you can use more principled approach like Bayes' rule and others to improve the target accuracy. And also, after you get the distribution of the endpoints, you can predict the error rate, which will be very meaningful in many applications. So I'm going to go through this procedure of how these authors derive the model, evaluation of the model, and also the application of a model. Again, let me just repeat. The model is taking the input parameter, which are target size or moving speed. The output model will be the endpoint distributions for selecting these targets. So actually this modeling-based approach has been widely used in HCI. For the static target selection, there's a model for predicting the movement time, the classic Fitts law, and also the model for predicting the movement time for the moving target. And also many years ago, Xiangmin and I proposed the Gaussian model to predict the endpoint distribution for static target selection. And this author's work is about moving target selection. So it's different from my previous work with Xiangmin. And also actually this work was based on the same author's previous work of proposing a model to predict endpoint distribution for one-dimensional target selection. And this work, they extend the model from one-dimensional target to two-dimensional targets. And for the one-dimensional target, they call it Ternary-Gaussian because actually they conceptualize the procedure by breaking down the distribution into three Gaussian models. Later I'm going to describe you which are these three Gaussian models are. So again, this is the core contribution of the authors. They propose this two-dimensional model that will predict endpoint distribution. They call it 2D Ternary-Gaussian model. And as a first step of deriving the model, we have to define the task. So what's the moving target task? Here shows example for in the one-dimensional case. You can see here you have selecting this moving target. You have a cursor. You have a starting point, and then select it. And the parameters of the task can be described here. That you have the A, which is the initial distance between the cursor position and the first time the target appear, and also the moving speed of the target, the V, and also the weight of target. These are three parameters for defining a one-dimensional moving target selection. And then if you move to here's the endpoint distribution. Okay, and then the focus of the work, of course, is on two-dimensional target selection. And two-dimensional target selection actually become more complicated. First, the target's shape, they change from one-dimensional, like vertical bar, horizontal bar, to two-dimensional shapes. In this case, in this paper, the authors focus on circular target. And also, the target could move in any directions, not just horizontal or vertically, could any directions. And see here, it's a direction, and also has speed, along the directions. And to further successfully model the attack, first the author, they define the coordinates they're going to use in the study. That they define the coordinates based on the moving object itself. So the x coordinates always point to the moving direction, and the y-axis point to the direction perpendicular to the moving direction. That's the coordinate they're going to use in this study. And then the parameters defining two-dimensional target selections are these three: the initial distance to the target A, and also the moving speed V, which is a vector, and also the size of the target, which is the diameter of the circle W. So the model, again, is basically taking these three parameters and will predict the endpoint distributions of the moving target. Okay, here's the core contribution of the paper. But how do we predict the endpoint distribution? First of all, we all know that endpoint distribution follow a Gaussian distribution. They use this yellow curve to show the endpoint distribution. Here, there's two vertical lines here represents the size of a target. This the middle dashed line is the center for target. So first of all, we know that the endpoint distribution follows a Gaussian distribution. And the core contribution of the paper that they break down these Gaussians into three components, and each component also be modeled by a Gaussian. So the beauty of the Gaussian distribution is that if we have multiple Gaussian distributions, add them together, and the sum is still a Gaussian distribution. And why they break down into three components? Because they hypothesize that each component represents one channel of uncertainty. And each channel of uncertainty contribute to the final distributions. So simply, you can use each Gaussian to represent each channel of uncertainty and add them together to form the final distribution. And here I'm going to dive into what are these three components are. The first component is called the size component, the green curve here. So this component is related to the size of a target. This means that the wider the target, the wider the spread is. It reflects the user's intention of utilize the target size to select the target. So this component is proportional. They hypothesize that the standard deviation is proportional to the size of a target. So this is the first channel of the uncertainty coming from the size of a target, because the user try to utilize the size, and they might spread the point out. And the second channel comes from here they call the V component, which is represented by the moving component represented by the blue curve. So this component represents the uncertainty comes from the moving speed. The basic idea here is that if you are trying to select a very fast moving object, of course you have more uncertainty. But if it's a static object, this component should have a zero variance here. And the third component is the absolute component That's the XA represented by the green curve here. So this curve represents the uncertainty comes from the input device itself. The underlying reason is that if you use a mouse or pen, it's be very precise. So this component have very small variance. But if you use a finger, and you tend to have the wider spread. So the basic idea is that they break down this fine ending point distributions into 3 Gaussian components, and each component represents a different source of uncertainty. And add them together, you have the final distribution of the endpoint distribution. Here, and also by adding Gaussian together, the final mean is the sum of the mean of each component, and the variance is the sum of variance of each Gaussian. So this is a property of a Gaussian distribution. That's the final equation of predicting the mean and the variance of a Gaussian distribution here. So you can see here the 3 components, and one is related to the size, one is related to the speed, and the other one is the absolute component. The variance is the variance of adding 3 components together, and they also hypothesize that the movement component and the size component are not completely independent, so there are some coefficient here added. And they further propose this model, and then the D, E, F, G are empirically determined parameter. So this is the model they use to predict the endpoint distribution for one-dimensional task. Of course, here the contribution in this paper, they extend into 2D. So in the 2D case, of course, we know you have the variance. You have there's a 2-dimensional Gaussian. You have X and Y component here. And for the X component, again, X component is about the axis along the movement direction. And then they simply use the same one-dimensional Gaussian model, which I explained in the previous slide. The challenge here is that how do you know the variance on the Y dimension? And then they actually propose 2 approaches for modeling variance in Y dimension. The first that they assume the Y dimension, which is perpendicular to the movement direction, only related to the size of the target, had nothing to do with speed. Second hypothesis is that this component also related to the speed. So you can see here, maybe speed also contribute to the variance for the Y directions. So these are 2 model candidates for Y dimension variance. And then they run user study to evaluate which one is more appropriate in modeling endpoint distribution. We have 13 objects and then 13 subjects and a large touch screen and different target size and speed. And they actually test 3 input devices: mouse, stylus, and finger touch. And the metrics, they determine which model is the better, use R-square, and also mean absolute error, and also mean Western distance. It's a distance that basically describes how close 2 distributions is. And their result shows that the model 2, which include the speed for predicting the Y-dimensional variance, has the best performance. They actually use the baseline dual Gaussian, which is for static target orbit object operation static target selection as a baseline too. Okay, so I'm going to later jump to the application for the model. Here I just quickly describe how they derive the model. Again, the model basically taking into the input speed and the size of a target, predict the endpoint distribution, the mean and the variance for Gaussian distribution. But how we can use them as model? Yeah, of course, the one usage that we can use them to describe the result. But secondly, actually shows that we can use a model to improve the target selection accuracy and also predict the error rate. First, because we can predict the ending point distribution, it means that giving a landing point, you can predict the likelihood of selecting this target given the touch point distribution. And then with that information, you can combine with the prior probability to predict the probability of selecting target. For example, here, assuming you are going to select one for these 2 objects, T1 and T2, and then your landing point is observed at S here. So intuitively, we use the boundary as a criteria. If the touch point fall outside the boundary, nothing selected. But with the distribution predicted, you can know that you can estimate the likelihood, like how likely you're going to observe as if T2 is a target. So this basically just use a distribution you can predict as a statistical, simple statistics. And then there's a likelihood. And combined with the prior probability, with the Bayes' rule, you can predict the probability of selecting a target, giving an ending point here. In this case, also assume that all the prior probability are equal. So you can simply use likelihood to represent the probability of selecting a target here. So they actually run a study. It's called the Bayes pointing method. They run a study with 16 projects, selecting different moving objects on touch screen. And also they compared with other previously proposed methods like bubble cursor or comet. For selecting moving target, the baseline is the one simply use the boundary to determine whether the target is selected. It turns out that the Bayesian-based method with the Ternary-Gaussian model has the lowest error rate. And also, the second application that you can use this model to predict the target selection accuracy. The idea is simple, because currently we determine whether target is selected or not simply based on whether the touch point land into the target. You just calculate the probability of the touch point within the target site. That's the error rate here. And this obviously have a lot of implications for UI design. For example, you can predict whether the UI is properly designed based on the error rate. Okay, they actually run a study to evaluate our model with a moving end selection target. Turns out that the estimations are all very close to the actual error rate. Again, I think I want to just emphasize the one major contribution of the paper that they propose a model that taking into target site and moving speed to predict the endpoint distribution, basically the mean and the standard deviation of the Gaussian distribution. And from this predicted distribution, you can use Bayes' rule to improve touch accuracy and also predict the error rate. So that's the end of the paper. I'm not the author again, but I feel honored to present on behalf of them. I'm happy to answer any questions if you have. Yeah, thank you.
So we have time for one quick question. Okay, so can you talk a bit about, like, if you know what the future directions that the authors are planning to take?
Yeah, I feel it's what I really like about paper is that they break the uncertainty into different channels and model them separately. I think future I can see you can either extend them to, like, for example, modeling like 3D target operation, maybe have more uncertainty in different dimensions. So, and also this model-based approach, I feel it's a very promising way of improving the touch interaction. Yeah, thank you.
Thanks.